Eu pratiquei. E aí, mas não sabe.
Não, o pessoal tá combinando no zap, né?
Quantos que eu sei?
Tinha o pessoal perguntando lá do
Como é que tá?
Ó, inclusive fiz
Muitas épocas.
What's this reaching the risk file?
Desculpa.
Why not?
É mais difícil em Campinas.
Nossa, não chegou mais cedo.
Não sou cedo hoje.
Você me sempre
Vamos pedir uma carona pro Guilherme. Eu falei, o cara falou assim, eu posso parecer sentado, mas não sei.
Não, e sentado, você falou isso que era, eu falei.
Eu vou sentado, precisa ter no computador.
O cara tem que ser monstro, né? Tem que ser aquela marca que você tem o olho sentado. Porque eu falei.
Ele é velho, né?
Mas eu adoro, mais confortável, menos aquele negocinho mais alto.
E aí, sim? Peraí. Que a apresentação fica no PowerPoint online. Se não tiver online, a gente não consegue ver o PDF.
Amarelo. Esse tamanho logo.
Na verdade, deve gerar isso lá no Microsoft e fazer o download no seu computador.
Realmente, tá aqui já.
Ah, sim, porque você está usando o PowerPoint. Você não está usando o online. Se tivesse está aqui, não faz sentido nenhum. Está aqui já. Sim, está tudo aí. Você tem o arquivo PTX aí.
Ele tem a parada assim, a gente não vê com frequência. Isso, não vê. E é curioso porque no vídeo, eu acho que não
Depois eu coloco no transar.
não demonstra.
O que você acha?
É para funcionar. A única coisa que
Não tem HDMI. Esse é HDMI?
é HDMI. O problema, eu preciso ver como é que tem que fazer isso lá no OBS. Porque hoje em dia... Não, é para funcionar. É para funcionar. É para funcionar. É para funcionar. Podemos tentar isso então. Beleza? Bom, Ó, Fred, você conectou no YouTube aí? Tá transmitindo? Como é que é?
Você falou do João?
Não, o YouTube. Não. Eu vou começar aqui. Achei que você conectava.
Eu já abri o e-mail, apareceu o e-mail, já está respondendo.
Só preciso ver se você não.
Por isso que eu peguei um que já fosse legal. 2 vezes. O cara tem uma operação muito.
Pegar um tape de 1968. Aí quando chega lá, passa o cara pelo computador. Olhando o aleatório X e tal, e uma média, mediana, foi integral, derivado, aí eu fui comprar um livro estatístico. Tinha uma galera aí da faculdade e tal.
A faculdade já sabe isso, essa parte difícil que eles não sabem, eles são comando.
Mas eu não sei.
Ah, sei. O pessoal sabe, o kit dele eu não sabia. O bando eu descobri. Então, tem as coisas do kit. Então, assim, vou ensinar kit, eles não sabem que você bate. Os caras, chorando, da hora. Eu espero que eles sejam entendendo a minha palestra. É super simples para vocês. Tipo, F3, sabe? Ok, F6. Mas não dá pra fazer isso com cara. Alguém precisa impressionar, sabe? Espero, né? Aí só tem você. Você não parece pra ninguém.
Não, mas ele macete tem?
Não.
7, e aí se não tiver mais uma base, tem que gravar. Depois a gente tem a base.
Só vou começar só para tentar manter o horário mais ou menos.
Fazer backup.
Good morning, everyone. Welcome to FOSForums 2025 third edition this year. I'm quite happy that we were able to organize this year. My name is Leonardo Garcia. I work for Linaro, and together with Rafael Seni, we have been organizing this conference for 3 years now. Free and open source software and hardware. So the idea is really to share and discuss projects and ideas around free and open source hardware and software that are being developed in Brazil. We will have a dev room this year. This is something I was looking for. Actually, I have some slides, so let me move on. Anyway, so before I go into the dev room, so this year, same principles as past years, right? So focused on free and open source hardware and software, as I was mentioning. Free to participate, so there is really no fee to be here. We had around 40 registrations this year. There will be a joint session in the afternoon at 2 p.m. with the seminars that usually happen every Friday in the Institute of Computing here at Unicamp. So there might be more people on that session at least. English as the main language. We believe that this is the only way that the work that is being done here in Brazil can be propagated to other places. And this is the only way to get engagement from others in the international community to the work that we do here. And yeah, located in the university. Now, past years it was during a weekend. This time we decided to try to do it on a Friday and a Saturday. Didn't work quite well as we were expecting, but at least Friday we are here and we are really testing if it will work. I already had some complaints about that, so this is definitely going to be something to be discussed for next year. But anyway, we are here and that's the important part. As I mentioned, for the registrations this year, 8 presentations. I had to reject some of them because we were not able to fulfill 2 days, but yeah, it was a difficult decision, as I mentioned to some folks, right? So we decided to focus on 1 day. We will have a dev room. The dev room will be about QEMU development. It's something that I was willing to have since the first year, but unfortunately it's quite difficult to organize, and we need to have someone very committed to deliver this kind of hands-on activity. I'm very happy that Mateus is going to do that this year in the afternoon. So yeah, I hope it will work well. He will teach something that is really difficult to find. I mean, some kind of skill that is really difficult to find in the industry. So if you are trying to find a job in some very specific area where there are probably less than 10 developers in the world doing this kind of work, you should be there, right? We have 9 presenters this year. Thank you very much for all of them. Code of conduct. We don't have any specific code of conduct described in any place. We believe that Brazil has enough laws about that. So if you have any issues, just contact us, myself or Rafael, and we will happily address them. So yeah, we think there is enough about that in Brazil. So next one. Data privacy, we will not share your information. As you saw in the registration, we just asked for the email and the name, if I recall correctly. And that's only because we need to do registrations. My real desire was to have no registrations at all, but unfortunately this is not possible in Brazil because we have to control how many people can come to the places. Anyway, so yeah, we will not share information, but we will take pictures during the conference. So if you have any issues with that, just tell us, because we will need to remove you from the photos, which is quite easy these days with AI. Just a minute to thank our partners. So I work for Leonardo. Leonardo supports the organization of this conference every year. Rafael works for Risk5 International, and they support the organization as well. It's probably one of the few places where you see Leonardo and Risk5 side by side, but anyway, and maybe on open source conference as well. Unicamp, of course, and Institute of Computing, because they are always, welcoming us in this space every year. And the Instituto para a Conservação das Tecnologias Livres, they help us to fund the conference and to organize our finances. So talking about a little bit about them, you might be familiar with the Free Software Conservancy, if I recall correctly, right? Yeah, thank you. It's very similar. The idea is to have some legal entity in Brazil that can support conferences. Sometimes when you are organizing conferences, the sponsors, they don't want to donate money to the person organizing the conference. They need a legal entity to sign a contract or something like that. So ICTL can do that work for you, and they help us with that as well. They also organize some other conferences. So Debian Brazil, FOSForums, FLUSP, and they used to help with Linux Dev BR as well. And DebConf 19, they were the ones that helped organize that. Right, if you want to know more, they have their website. I really want to thank you, all the people that helped to organize this. So Rafael, of course, that is always helping myself to organize. Rodolfo, Professor Rodolfo is the one that usually help us to, reserve this space and have us being here. Sidney and Bruno, the guy without a photo, are the guys from the infrastructure here. So they help with the audio and video, all this nice infrastructure that they have here. Charles is not going to be able to be here today because he had a conflict, but he's always supporting the conference and trying to participate. Gabriel, the other speakers, right? Gabriel Cascardo, Tadeu Cascardo, Guilherme, the guy with the paper head. Oh man, what is the name of the other guy? Carlos, if I recall correctly, yes. Usama will be our first international speaker. Unfortunately, he's not going to be here. He will be remote, but I think it's going to be quite interesting. He will talk about confidential computing. Giselle, who will be speaking in the session that is going to happen together with the seminar. Mateus doing the dev room, and Antonio and Daniel, they are the guys responsible for ICTL. So thank you very much for all these folks that helped to make this happen. And I hope I didn't forget anyone. So this is the agenda for today. We have a quite busy morning and a more light afternoon with the dev room closing. So not sure if it will be that light, but yeah, so we have a lunch break at noon. There are lots of restaurant options around. And we will have a coffee break at 3 p.m. as well. I think that's it. If you have any questions, you can reach out to us, and the schedule is in the conference website as well. So this is just a map for the ones that are not familiar with Unicamp. So we are somewhere here on the blue dot over there. There is a restaurant at Unicamp. There is the university restaurant over here close by. So you can, and there are many other restaurants. If you have any doubts, you can just talk to the folks here. And yeah, we do plan to have another FOSForums next year, last weekend of August again, or last Friday of August. We need to decide that. But anyway, so do expect us to hear from us next year. And with that, we will go to our first speaker, Rafael, who will talk about open collaboration in action, how we make RISC-V. Eu não sei por que ela tá, mas eu tô gravando.
E sua apresentação? Ah, sim. Okay. So this should be quick and straight to the point. It's more about how we're making RISC-V and what are the opportunities to where anyone can engage, and what we do on a daily basis that and why we do that on a daily basis, and how complex it is to manage an organization with over 5K members, with all major players in the market trying to sell their ideas as the best idea to get implemented as a extension or as a standard. But before we go to that, I'm just mention some highlights. Some of you, I believe, saw that before, but RISC-V is already on cell phones, is already on cars, is already on, it's not already here, because that's why it's slow, is already on laptops, is already on wearables, data centers is coming, especially on accelerators. We see a huge trend on AI, given AI, on how things are going, especially on customized accelerators for specific workloads. And then, of course, AI workloads. So it's getting everywhere. It's no longer a matter of when. So we see companies already selling hardware stuff to major companies. This year we had the RISC-V event in Brazil, where Petrobras signed some agreement to start buying some RISC-V based accelerators with a lot of cores. So they're going to start getting that, not just Petrobras, but also LNCC and other public institutions in Brazil that requires some accelerators to try and come and say NVIDIA alternatives as they depend on those resources. But anyway, RISC-V is growing. Most of that is because now we see a huge push from verticals. So every area there's a specific need for every area, and they are pushing that with RISC-V. Here we can highlight at least three: automotive sector with a bunch of companies in Europe driving that, and companies that were created to push that on RISC-V platforms. Space, there's a bunch of work being done on space right now. And when you think about space, is NASA, is Airbus, is Embraer that's doing project with RISC-V already. So all those companies are now getting together under RISC-V International, under a SIG called the Special Interest Group for Aerospace, where they're going to discuss how they can use RISC-V or define pattern or standards for that sector. And of course, we have others, AI, HPC. So every major vertical is adopting RISC-V and come up with ways to use that and create standards around that. That's why RISC-V is getting a huge push nowadays. You'll say even more than it was getting in the previous years. This is not new, but anyway, the prediction that by 2031, around 25% of the market will be running RISC-V. And for some markets, yes. For others, we think that's not going to happen. But anyway, that's the trend, and we see this. We see on a daily basis a bunch of activities that support these graphics. And why RISC-V is so popular? Because we are in a place or in an area where software and hardware co-design where we can get the best advantages of that. So we see a lot of companies making custom accelerators, for instance, for specific needs, and tying that with a specific software so they can leverage the best or get the best performance as possible. This is one of there. So given RISC-V is a standard, you can take that and do anything you want. You do not need to pay royalties, you do not need to pay license. Of course, if you are willing to pay to buy an implementation for a given company, you may need to give them some money. But to use RISC-V as is, you do not need to do anything else. Just grab the PDF and start making your design. And once you adopt an open standard that's really good enough, you don't go back to a private or a closed source. And we saw the history showing that. So this is also not new slide, but you saw that throughout the history, a lot of those closed source or private kind of implementations were replaced by standard open standard when the open standard became really I would say mature. And this is a research that will I'm work at Linux. I'm a Linux Foundation employee, work on RISC-V International, and this year we launched an updated version of the open standards and what's happening around the world when open standards are applied, how open standards are solving problems. So this is an interesting paper to read. It's not a paper, it's a research that is interesting, that shows how things are going on and how people are adopting open standards, how that innovation is growing with open standards. Given open standards, we see things happening quickly. So countries are using, in case of open RISC-V, for tech sovereignty. So every single nation, not every single nation, but we have United States with NASA, we have Europe, we have China, we have India, we have Brazil, a bunch of countries that are now dependent on RISC-V or are setting RISC-V as key part of their roadmap for tech sovereignty. For multinationals, like for instance Qualcomm, they are relying on RISC-V to control their strategy, their roadmap. Not just Qualcomm, but we have a bunch of other companies that are now putting RISC-V as a key technology to ensure they can succeed and have better control about what they're doing. For researchers, and if you go to ArcsV, for instance, you're going to see the number of papers that show up on every week on a weekly basis, to be honest, about RISC-V, using RISC-V. So that's opened a lot of opportunities for them to do something new and publish that quickly without handling any bureaucracy, for instance. And they are supported by a bunch of open source tools that help them make what should be done. And for startups, if you see the number of startups that are part of RISC-V International is really, the number is really big. And the number, especially on number of design houses that were created, given they are able to use RISC-V, is really impressive. So it gives, when you start to use RISC-V as an open standard, that opens up a bunch of doors that you can start playing, and in order to make what should be done, and gives you the freedom to do anything you want. And I mentioned about what's happening across the world, so it's not news. It's not new news for you all, but we see that all major countries are use RISC-V. In Brazil, that's interesting, and I would like to highlight. This is a website that was launched yesterday, not yesterday, but this week during the conference called "Chip in the Jungle" in Manaus. It's coming from the Brazilian federal government. Brazil now is, from basic education to the point where they can form entrepreneurs. There's a path that you can start learning about semiconductors, learn about how to make chip, whatever you need to do, and grow step by step, all supported by public program. So for some of them you can get paid to be part of, but essentially they are all free. And I'm proud to say that in the last 2 years we managed to put RISC-V in every single one. So all major programs from the federal government, Brazilian federal government, are teaching use RISC-V, which is good because, if you see the results, so a bunch of individuals, if you look at happening, the south of Brazil, especially Rio Grande do Sul, is where most of those individuals are. And Rio Grande do Sul is becoming our semiconductor, center, or center of excellence, if you will. A lot of those students there are now starting to fly abroad or starting to get internship abroad because they are leaving the CI Inovador program from this year and getting not jobs yet, but getting internship opportunities in China, Malaysia, Europe. So there is a interesting kind of collaboration that's happening right now. But anyway, you see that Brazil 3 years ago decided to take this step and embrace RISC-V. Now it's propagating across all the programs and also on the strategy. It became so important that other ministers, not just the Minister of Science and Technology, are talking about RISC-V with the president for now. So they are managing to put RISC-V as a top tier technology for Brazil to happen the next year, which means or translates in more investment for local companies or for research and development. So RISC-V is growing. This year, RISC-V completed 15 years. So there's an interesting blog about that. So you can see what's happening, and why it's growing so quickly. But this is not about RISC-V itself, but how we make RISC-V. So we see news about RISC-V every single day. We see companies adopting. We see they play RISC-V. We see companies, other companies complain about RISC-V, grow, and try to shut us down from time to time. But how we make that, and why people are part of that? Essentially, we're built by a community. So we, as I mentioned in the beginning, we have over 5K members. And those are individual members, companies, big companies, small companies, startups. They all come together because they want RISC-V to succeed, because for them that represents business opportunities at the end of the day and how they make money. And that's why they allocate really expensive engineers to make things happen. When I say really expensive engineers, so the creators of RISC-V are still behind most of what we do. And they are company owners now. So, but we have key players from Google, NVIDIA. I believe you heard the news about NVIDIA porting CUDA to RISC-V. So there's a lot of things that's happening, and we have a lot of people. As a community, we have a lot of egos. So handling that is the most difficult part, because we have a lot of really skilled individuals that are willing to push things forward, but some of them are willing to push their ideas forward, not collaborate, because they come from an environment where deciding quickly make things happen is more important than collaborate and make things happen with multiple hands. But anyway, we are built by a community. And essentially we work on the base layer, everyone works here. And from here, we define the base ISA, the base extensions, everything should be done, or everything that should be part of the major documentation. And from this point, any company takes that and make what should be done. Some will create open solutions, and others will create closed solutions. That's up to them. I mentioned about a lot of countries, of course, a lot of companies. We have more premier members joining this year, so some of them we can't announce. Some of them joined and does not want to be associated with RISC-V yet, because that could impact their business. But they joined it, and they do not want to publicly disclosure that yet. But when we do, that will be really major news for the whole world. But anyway, I can't say anything more. Otherwise, that would be a huge problem. But anyway, things are growing quickly and in an interesting situation. In RISC-V, we are organized like this. We have the board of directors that oversees us from the business point of view. We have the technical steering committee that oversees us from the technical point of view. And then we have some special groups like profiles and server platforms, but we essentially everything else is under these kind of horizontal committees, like as we call them. So you can see these like organization in a company or a department where every task group or SIG is added or included, connected to those items. And we have 6. We do not plan to grow that more. We have those privacy and private committees that manages the or oversees the specification from both point of view, and those are the two most important committees that we have, because we have the founders of RISC-V there, and everything we do in the other HCs and TGs and SIGs needs their blessing from time to time. So they are our lovely bottleneck. And the CTO and us and myself, we are overseeing everything that's happening here and there. And now we are pushing for another committee that's going to handle RISC-V certification. So this is how we organize from a higher level. Today we have around 22, we have more than that now, but actively working 22 special interest groups, 24 task groups. They are touching different areas and different needs. The highlight here is more for the matrix stuff. So we have 3 task groups working on matrix extensions. So we have IME, attached matrix extension on how you can pretty much define the pattern or the standard for your external accelerator. We have the vector matrix accelerator, and we have the integrated matrix extension. So at the end of this year, hopefully we're going to get the best set of matrix instructions available for anyone to use and apply as part of those accelerators they're creating. So a bunch of task groups, a bunch of individuals, a bunch of people work on those areas. This year we created 70 more. So, and my work is to manage them all, essentially. I work with them on defining the priorities, defining what they need to do, track what they're doing, when they're delivering, how they're delivering, and we need to manage all the individuals here. So as I said, it's a bunch of senior engineers that come from those companies, and from time to time it's not easy to handle their how they would like to work, because somehow they do not see us as their, and we are not their bosses. So we need to help move things forward in a way that they understand we are collaborating, not pushing them all the time. But anyway, it's growing. Here, a highlight from here is the automotive SIG. We have the space SIG that's not listed here. It's there, as I mentioned. RVM profile for microcontrollers. So things are, and server SoC version 2 that's going to work on the set of tests for the server SoC that specification that was ratified this year. So we have a lot of things happening this year, and we have more coming. I believe that we're going to double the number of TGs this year, which is a good number. So how things start, how a technical committee is created. We changed the policy this year because until the end of last year, anyone that had an idea could propose a technical committee and start doing things. And that created a bunch of technical committees that that died, because one of the hardest part of RISC-V and how we make that is from time to time people change company. Not from time, but very often people change companies. And someone that was leading our work a given moment move it to company, another company, and that person no longer able to manage that. And then we have an open position that no one is willing to fill, and the work dies. What we did with the new policy, so if you want to propose something new, you need to get at least 3 premier or strategic companies supporting that work. So for instance, today, if I want to propose some new SIG, I need to reach out to all members and get at least, let's say, support from Google and NVIDIA, and a company that's like Ventana, Rule, for instance, that is a strategic. Without this blessing, without this support, no one can make anything. So that's important, because with that change, we want them to commit resources to the development that's giving work that should be done, and ensure we deliver that. When they do that, they start proposing that. There's a bunch of approval that's happened. The process became a little bit more bureaucratic now. So usually this would take 1 month. Now it's taking 3 months to get to the proposing phase, because we need to get their proposal of work, get those supporters, put them in front of the technical steering committee for presentation, then get approval from TSC, get approval from the board of directors, and move things forward to the next phase. So, which is they're going to start a more bureaucratic set of activities on the structuring, defining voters. It all came about with the new policy, the voter kind of approach. We didn't have that last year. The elect chairs, develop their charter, and again go to TSC for approval. Then they go to the active state, where they started developing the work, but until they reach the active state where they really are able to do the work, is going to be essentially 3 months until we can get people to really do our real work. Some complain about that. We do not complain about that, because that improved a lot the quality of the proposals and in the assessment about a given need. We no longer allow people to just do things for fun, or because they want to get a better review from their employer by the end of the year, and they want to be part of RISC-V and show that they are leading some work. When they, so when they do that, they start to work on some activities, and pretty much the result of that activity are delivering ratified specifications. So far, we have 10 this year. I think we have more too that came yesterday, if I'm not mistaken. We plan to get around 20 plus specifications this year if everything goes well. But to develop this, I need to talk about this. But what happens? So when those TGs or SIGs are created, they're going to work on some of this area. Some of them can work. Some of them can work on change the core assay, for instance. It works. The core assay. Some can work on an ISA extension or a non-ISA. With RISC-V, no one do custom extensions, so we do not ratify custom extensions. And then we compose those extensions as profiles, can be RVA. Well, this year we're going to have an update of the RVA profile and RVB. Those are the profiles that aggregates a bunch of extensions that the major operating systems are adopting and supporting. And now this year we're going to have our RVM also. Oops, sorry. Yeah, and then we also have the profiles that are explored and adopted by platform servers, so anything that should be doing. So anyway, someone propose an idea that get approved, they start working, they pick what they want to do based on ISA or no ISA. So later we integrate that as part of a profile, and then once that's integrated as part of a profile, people start using that as, according to their needs. But how we make a specification? So usually a specification or getting a specification done takes about, or the minimum 1 year, even for a simple specification. So we have two approaches to develop a specification. One is creating a task group, for instance, to drive the work. Or if the specification is really kind of small, we call them fast track, where we skip the process of creating a new TG and make things happen quicker. But usually you are saving 1 or 2 months only. But anyway, when they start developing the specification, there's a bunch of activities that should happen throughout the life cycle. So they need to get a plan, they need to get their plan approval, and approved by a bunch of people, to be honest, and until they start the real work we should develop. And that can iterate throughout version 0.1 through version 0.6. Then they need to stabilize their work, they need to freeze the specification. Once the specification is frozen, that means we do not expect major change on its content. Of course, small fixes are allowed, but you can't change the meaning of the specification, you can't change the normative rules there. But you can do some minor tweaks. And then we go to ratification ready, where the key activity there is a public review, a 30 days public review. And this publicly means everyone in the world should be able to provide input on that and provide feedback. Usually you do not get a lot, that feedback comes more from members, but anyway, it's part of the process, it's part of the open standard, especially now because we are closing and getting aligned with ISO, what they do. So we are becoming a ISO standard this year, and that requires more bureaucracy that should be implemented from the process point of view. But anyway, and then once the specification gets the final approval, we move to publication where we get the board approval. So this process, even though it looks simple, usually takes 1 year. We have specification that took around 3 years, 2 years, 1.5 years. It depends on how much effort they want to do or want to put on that, how much effort they're willing to, or how much fast they're willing to make that move. We move as fast as those chairs want to make things move or want to make things happen. If we start a specification today, you can get that ratified by in September next year. So assuming there's no delays and though there's no issues happening. And by the way, I created this tool using Vibe Code, using ChatGPT. Yeah, it was fun to do that. And not a web developer. So anyway, that's a huge process that they need to go through to make things happen. So it's a long, long process. And we have a lot on the fly right now. The main ISA, so just mention that there is a process on how the main ISA is done. It's not complicated, but we are getting all new specifications. ISA specification is a fork from the main ISA until that fork gets stable, get ratified, and then we get back the fork into the main ISA. So it's not complicated, but pretty much we took a while for them to understand that this is how we need to operate and no longer doing merge directly in the main ISA. But anyway, we're getting there. Opa. But how to participate? How you can be part of this? Yeah, you need to be a member. That's the primary criteria. So without being a member, you can't contribute to the development of the specification itself. If you want to become a member, or do you need to be a specification author to be part of SC5? No, because we have a lot of opportunities for engagement. So you can also join, you can select the SIG. So if you are willing to play or to see what's happening on the HPC sector, join the HPC SIG. If you want to play, see what's happening on the matrix groups, join the matrix group. So anyway, join SC5, pick what the area or the task group that you want to be part of, start engage. Pretty much a typical kind of open source stuff. Everyone knows how to do that or understand how to do that, and there's no complication or issues on that one. But how you can get involved? So throughout the development process, so the idea, someone starts with the idea of a spec and then propose that, just find a plan and start to work on that. We have a bunch of work that's beyond writing the text, defining what the specification is, what the instructions are, and how they should behave. We need help on getting implementation of simulators. QEMU, we have the golden model, which is within Sail. We need to get contributions made upstream the kernel, GCC, LLVM. So everything that should be done or put in place to ensure that anyone in the world can grab that specification, try that, and provide feedback should be done during the development process. So if you are not a specification author, but you want to get engaged and one is willing to help, and you're willing, for instance, you are willing to get or learn about how to do kernel contributions, start helping us, because usually the contributions are not that big. So it can give you some roadmap about how to contribute, how to learn about to do that. The same with GCC LLVM. So we depend on that a lot. If you want to grow your skills there, or to get some, let's say, become more influential, and you want interesting work to do, so you can join RISC-V and help us drive that work. So there's a lot of opportunities for software developers right now to help us, because as we mature on RISC-V, we are going to need individuals that understand the architecture or understand the ISA and help other companies port and optimize their solutions to RISC-V. So as early as you get the information about a new extension and understand how that behaves, and understand how to take advantage of that, you create an interesting technical advantage for yourself and maybe for your employer if need be. But anyway, if you want to contribute, there's a lot of opportunities. You should join a task group and to make things happen. And by the way, this guy here, hang on. This guy here is José Moreira. He is a Brazilian that works for IBM United States, and everything we're doing on Matrix today get his blessing. He became one of the most important individuals in RISC-V today, even though he works for IBM, even though he's driving the IBM Power processor. So most of the things we're doing here, the idea of Matrix start with him, provide or share with us what he did for IBM Power 10 and MMA. Of course, he didn't share the details, but share the idea. And now that's becoming one of the standards of RISC-V. So anyway, in addition to Jose, we have Professor Guido, that also helped to drive and start one of the initial Matrix groups. So there's a couple of Brazilians doing good work there and driving the RISC-V, not just being part of that. So as I said, as we move forward to the specification development, there's a bunch of tests that should be done. So if you are willing to contribute, be part of RISC-V from a technical point of view, you do not need to be a spec writer, just raise your hand and be a volunteer to help us define some of those. Even help on documentation, review some documentation, fix some. If there's a new student that's willing to start to learn how to do open source, help us with some typo, text, improve the text. Anyway, there's a bunch of opportunities to help us there. As I said, so a lot of opportunities. And how you can learn about RISC-V. So just quickly go through that. We have a bunch of courses and training, so you can pay for some, get others for free. There's a lot of good resources listed on this repository here. I started this 2 years ago, and now it's an interesting repository with over 1K stars on GitHub. So there's a bunch of things listed there, and there's a bunch of students from Unicamp that contribute to that repository also. Engagement opportunities. In addition to develop the spec, so you can teach a course. Usually we pay a good amount of money for those that are willing to decide or define and create a new course for RISC-V. You can become a mentor or a mentee. I'm running mentorship myself for the last 2 years, and I usually get a good number of applicants for that. It's a good opportunity if you want to educate or share your knowledge with someone else. You can become a training partner, so if you want to get something organized or your company is providing training, so you can become a training partner. We have the ambassadors and advocates program, developer boards. If you want a board, maybe we can ship something to you. We have labs that allows you to access RISC-V in the cloud. Those are pretty much similar to the mini cloud that we had here at Unicamp for a long time. We have, RISE Developers Appreciation that kind of bounces us to give you some money to develop there, solve some small problems. You can engage on the summits. So the next one is in October in Santa Clara, United States. Hang on, let me go back one slide. This one here is the next one. But throughout the year, we have the summit in Europe. This year it was in Paris. We have the summit in China, and we are growing RISC-V in Brazil. So this year in Brazil, we had 2 events. Oops. One in São Paulo, both events in the same week. One in São Paulo called Grow. It was more bilateral kind of event between Brazil and China. So a lot of those researchers that are pushing RISC-V in China came to Brazil, and they met the researchers in Brazil who work on RISC-V. So it was more academic event, but it was interesting because it was the first one supported by both governments, Chinese government, Brazilian government, with a good worldwide kind of noise. So even the United States was concerned about what they're doing here in Brazil during the growth. And then we had the RISC-V Brazil at Eldorado Institute, the 2nd edition. So and this year we started the World RISC-V Day, that we were supporting small countries and small cities to get some event or collocated event where they could just discuss RISC-V. So that's an opportunity for engagement also. And I think that's it. So the idea here is to help on show you how we make RISC-V and show you how you can collaborate and how those individuals that are part of those companies that are members of RISC-V are engaging and collaborate. So if you want to help, just join RISC-V and start helping us. There's a lot of opportunity. So, and if you have questions, I can answer some questions, I think. So thank you very much. Any questions?
Any questions?
Any questions?
Can you talk a little bit about the mentorship program?
Yep. So usually we open a mentorship 2 or 3. I think it's 3 times a year. What we do, we open to any member. We invite the members first to propose a mentorship, and usually the mentorship is to solve a given problem. For instance, this year I'm going to start my 3rd one. The first one I did this year was on RISC-V in the kernel CI. So we needed to fix some stuff there and adjust how RISC-V was set in the kernel CI. But to do that, we had to understand what were our state in the kernel CI. So we propose a mentorship. I got 4 mentees for that, and we break down and start exploring kernel CI. What should be done there? Usually we have funding to pay 1 mentee, usually $6K USD for 3 months. So we pay during the first installment is in the half of those 3 months, and then at the end, based on the evaluation. The second mentorship I'm running this year, this ending now, is a continuation of the kernel CI. But for this one, for the first one, I got over 200 applicants, and I had to select 4. For this second one, still on kernel CI, I have less individuals. I got 110 applicants, and I was able to select 2. But this one, I got 2 really junior that never touched kernel, because I want to see how long it would take for us to get someone that's new to RISC-V, educate them on how to collaborate, and see them make effort. For the first mentorship, I got someone that was really aware and was really engaged with the kernel community, because we wanted to speed up the analysis. For the second one, how long that take? And it's really tight, because we're mapping how a student that never touched the kernel CI, never touched a Linux desktop, is going to take to do a first contribution. And my 3rd one that's going to start now is about software optimization. So anyway, we select. No, we're no longer accepting for the 3rd one, because I need to select those in there. I should have done that by yesterday. I'm late. But anyway, we do that. We select on 3 times a year. For the good ones, we pay around $6K USD for 3 months of work. So the best way to see what's happening is one is to become a member and join the mailing list, or keep watching our website, because we publish that every time we open mentorships. I believe for now we have mine. We have one from I do not recall. Not sure if that's one from Google, but Qualcomm is pushing mentorships and paying. I know Google did. I know Red Hat did. I know Ventana did. So we have a lot of companies pushing that. When we do not have funding, the company that's willing to push a mentorship is paying. So it's really hard for someone to not get some money out of this mentorship. Unless, I mean, for instance, this new one that I'm doing, designing but with the 2 newcomers, we decided to go with zero funding because we really want to test like the level of engagement. If you offer you nothing, just the capability or the opportunity to learn something, who will be willing to get that? And we are offering zero money, and I mean, I got 4 mentees. Out of the 4 mentees, 2 for me disappeared. That was expected, not complain about that, and we continue to do. So anyway, it's a good opportunity. Keep watching our website for the new mentorships that's going to open in January, if I'm not mistaken, and apply. So apply and send an email to the person proposing, because it's a lot of people. So if you can just send a nice message there, at least that works with me, because reviewing over 200 resumes and exercise is hard. So if someone takes the first step and say, hey, I did this, I need to do this and this and that makes our life easier. But anyway, it's a good opportunity to learn from others. I'm not sure if I answered, but anyway, this is how it works. And when we have time, we promote the mentors, the mentees. We organize some presentations for them to show their work. For instance, during the open source summit this year, I did talk about the work my mentees did. So I will give them the credit and build a stage where they can show off what they're doing. Because for us, one of the most important outcomes of that is, and my mentees, at least in this year, all my mentees got job offerings. A lot of them landed on Red Hat, and that's the only thing that we do. We help them with kind of recommendation letters, for instance, for the good ones, and try to match or offer them, but tell companies hiring that, oh, look at this person, they can be a good fit for your company, and we try to make that happen. I think we have time for one question. Any more questions or? No? No. So anyway, if you want to join RISC-V, if you want to know more how to collaborate, let me know. But anyway, there's a lot of opportunities, and you can learn a lot by being part of that. If you don't want to collaborate, just be part of that and watch what's going on. So it's a must-have knowledge nowadays. Okay, thank you, folks.
Beleza? Olha só.
Well, good morning, everyone. My name is Gabriel. I'm a master's student here at Unicamp. This is Julio. He also studies here. And we're both monitors at the Embarcatech, which is a professional training program for embedded systems. Specifically, today we're going to talk about a new track of the course, which involves FPGA programming. Okay, who are we? There are 3 institutions that are responsible for the course. Instituto Hardware BR Executive, and we also have Softex and Brazilian Ministry of Science and Technology. Well, Softex makes the bridge between the company and the government, and that allows Instituto Hardware BR to deliver many courses such as Sei Digital and others. But today we're going to talk about one of them, which is Embarcatech. First, what is Embarcatech? It is a professional training for students in embedded system solutions. They learn the theory, they learn how to use the equipment, and they learn how to create an actual solution using what they learned. We accept undergraduate students. We also accept people who have already graduated. And our target audience is engineering students or computer science students. And also people who have graduated in those fields. These are our training centers. We have two places where we have the students. One is here in Campinas, Instituto Hardware BR, São Paulo. The other one is in the Federal District in Brasília. And both places are executing the same course for the students. Embarcatech itself is much bigger, I need to add this note, and Embarcatech operates in more states than that. But the FPGA course that we're talking about today is at its start and it's operating just those two cities. The program has two phases. It has technical training and technological residence. The first phase is about teaching the students microcontroller basics. They learn the theory, they learn about IoT, they learn real case studies such as agriculture, industry, smart cities, etc. This part of the course is online. We have teachers and mentors connected through the internet. This phase has 1,000 students, and those 1,000 students are then selected to the second phase, and only 100 of those 1,000 are selected. The technological residence is mainly about practical activities where they actually can involve in activities with the hardware. And after some months of training, they work within companies in internships. This part of the course is hybrid, so they have some practical lessons at the training centers, but they also have online lessons at home. And I need to add something about the second phase, is that the students are separated in two groups. First group is about microcontrollers, where they learn traditional methods of using the hardware. They program using C language, they use RTOS, and etc. And the other group is about using FPGAs. And in that group, they learn how to create their microcontroller from scratch. They create the processor, they create the peripherals, and program the system they have created. What are the teaching methods for the FPGA track? First, we teach the students how to simulate their designs. We need to teach them the basics of Verilog and hardware description. And also we teach them how to use it to debug their designs. Once they're familiar with that, we can go to practical activities where they can use the created peripherals to interact with real hardware and use it in a real application. One interesting thing about our course is that all the steps of it use open source tools. The simulation part uses iVerilog and GTK Wave. When you're like building the first steps of your design or debugging it, Yosys is used to synthesize, turn the description to an actual circuit. And even the circuit board is open source. We're using ColorLight i9, which uses a lattice FPGA, and we've adapted it to the BitDockLab connectors. What is BitDockLab? It's another development board that the students of the MCU track use. So the FPGA board we're using is compatible with the microcontroller that is already being used in the other part of the course. Here are some examples of the peripherals that can be used in the course. We have lots of different ones. We have GPS in the bottom corner, as you can see. We have pressure meters as well. We have HDMI and other things. And as you can see, all the peripherals have a green board beyond the colored one. That green board is an adapter that can translate the original peripheral connectors to the actual BitTalk Lab connectors, which can make it much easier for the students to connect the peripherals and create their projects. Well, another cool thing about it is that we're going to publish the material. We'll need to rebrand it will not be Embarcatech anymore. The FPGA training will be available in the form of video lessons. We're going to publish it on YouTube. And also the activities will be put on a GitHub repository so anyone can learn without needing to apply to the course, or if is in another country and wants to learn as well. Okay. Well, to sum up what we have said, here are the course's differentials. Me, Julio, and the rest of the team are doing our best to provide high-quality lessons. We have a hands-on course. We have a lot of practical activities. The students actually get to use the hardware. It is highly connected to the market. We have internships for the students at the second phase of the training. We pay the students, actually. If they manage to get to the second phase, they get a scholarship, which helps them continue learning. And the institutions that are delivering the course are very well known, so the students are in good hands. Forgot to say that, but since we're trying to open the course and make the materials available, we think that will help the open source community to grow bigger and add more people to it. Well, how to participate in the program? There's no secret here, so I'll just read the steps together with you. First, you need to check the requisites. If you're able to attend to the course, you need to see what's your area, if you're an engineer, if you're working in computer science, etc. You need to choose the institution where you want to learn. In the FPGA course, you need to choose between Campinas or Brasília. Then, once you've chosen it, you can fill out the registration form and send it to us. And after some time, you'll receive the confirmation email, and then you can start learning at the course launch. And that's it. Very glad you took time to hear this presentation. And if you have any questions, you can reach me. If you want to know more information, you can go to our website as well. Thank you very much.
Any questions to Gabriel and Julio?
Yes.
How many loops there's the lattice FPGA that you're working on?
45K? It's a Lattice ECP5. Around 45K.
And which kind of CPU can you push to, like 80, 32?
Well, on the course, we've made a custom CPU, but for example, we have LightX, which is a SoC builder, and LightX uses the VEX RISC-V processor. I don't know if you're familiar with it. Usually, small embedded processors. They can run around 100 megahertz. Around 100 megahertz, and RV32IM C, stuff like that. Embedded course.
15 or
It's more like 50 megahertz than 100, but that's around it.
All right, thank you.
Okay.
grande FPG, né?
Você recebeu a máquina grande do live?
O cara tá na do Rodolfo ainda.
Ele vai usar? Não precisa botar a plaquinha? Antes de começar a usar?
Acho que começou a montar em cima e tocar as outras.
A máquina deve fazer bastante coisa.
Tem bastante corda.
É bom para otimizar os kernels de Linux, porque tá precisando.
Já tem precisando mesmo. A Nuke 5 eu comecei a mexer na caralho. Dá pra fazer bastante coisa ali. Preciso fazer um cantinho do Risk 5. Inclusive a gente escreveu um paper esses dias e parte dos experimentos a gente rodou no Risk 5. Tem que evoluir bastante ainda. Aquela Nuke 5 ela tem mais ou menos um nível do Pi 4.
Os cores que foram lançados esse ano na China são lindos. Nossa. Ah, você ligou ela?
Chegou a mandar coisa nela.
Foi de boa ligar ela?
Tá de boa. Só um cara interessante, eles dão um Ubuntu e um Fedora, né? Aquele Ubuntu, não existe mais, aparentemente.
Não? Ué, você tem que falar com o Sam, né? O cara
Usa um microfone? Melhor.
Que é pra ser custo, eu acho. Tudo oficial. Então, dessa deixa eu fazer mais pra frente.
agora com o suporte social.
Vai gravar o nosso conhecimento.
Daqueles caras que agora no Ubuntu
Hello everyone, my name is Tadeu Cascardo. I'm going to talk to you about Linux memory management, just a quick introduction. I'm going to go over a few topics. The Linux memory management is a huge part of the kernel. There are many pieces, and this is the agenda that I'm going through, but notice that I'm not going to talk about the MMU, about VMAs, about mapping, not much from the user space side. There are a lot of other topics around memory management that we could talk about. So I'm going to concentrate more on the side of page allocation and memory reclaim. So I'm going to talk about just a quick recap of virtual memory and how Linux deals with that. And then I'm going to talk about what Linux deals calls zones and nodes. Then just a quick talk about kmalloc and ZAPs. And then I'm going to the bulk of the presentation, which is get free pages and kswapd, right? So virtual memory, I assume most of you are familiar with it. So the processor addresses memory by physical address, but the software is using virtual addresses instead, and memory is segmented in page frames or pages, and we can look at the operating system in two possible ways, right? We can view the operation system as a virtual machine. So the processors see a single contiguous address space. They don't need to care about what's below the system. Or we can even see the OS as a resource manager. So we cannot even have all the memory that the program seems to see, like you may have only 4 gigabytes of memory, but the program thinks that you have 32, and the OS is managing all the resources behind it, and doing what we call paging or swapping, right? So this is how it may look like from a program perspective. It will have many different segments in its virtual address space, and each page is going to be mapped to a physical address. They're not exactly contiguous, and there may be gaps and pages that are used by other processes and things like that. Just like I used the image from the Media Week Commons, and this is the copyright. Linux, how Linux deals with that virtual memory mapping. So from the user space side, it looks like the image that I showed you before. The mappings are not contiguous in physical memory, but inside the kernel, most of the memory the kernel addresses uses what we call a linear mapping. So it's only an offset from the virtual address to the physical address. So it's like the kernel does not map memory uncontiguously. It's all a single mapping to see the entire physical memory. However, there are some specific scenarios where the kernel needs to have access to a very large contiguous memory virtually, but do not require that it be contiguous physically. So in that case, it uses what we call the vmap region by using an API called vmalloc. So there's a separate virtual memory space where the kernel can have a non-contiguous mapping. So here's like a quick recap of how the page tables work. This is more to talk about real quick what we call about huge pages. So usually we have multiple levels of translation done by the CPU until you have a translation from virtual to physical address. But in some cases, and then you have the offset inside the page. So this is x86 case here, which has a 4K page. Other architectures may have different page sizes. So PowerPC has 64K. ARM, you can have like 16K or 64K as well. But in the case of x86, we usually work with 4K pages. But you can skip one of those levels and have like a full 2 megabyte page, which is called a huge page, and Linux supports that as well. But well, let's talk about what Linux understands as zones and nodes. First, let's talk about nodes. So we have what we call a non-uniform memory access, NUMA. So to those who don't know what NUMA is, the quick explanation is that if you have multiple socket systems, you'll have multiple CPUs, and each one of them has a memory bus. You can have one memory connected to one socket, and when the second socket tries to access that memory, it needs to go through the first socket, and that introduces different access time. So usually what you want to do is that you want the CPU to access local memory. So whenever a process is running and tries to allocate memory, you want to allocate it locally on the memory that the CPU has the fastest access to. So that locality is taken into account when you try to allocate memory. And also Linux has the concept of memory zones. So there exists mostly to support DMA and high memory, right? So I think that's one of the reasons why it's useful to take a look at this translation here. Is that this is specifically the translation that is done on 32-bit x86 CPUs when you have PSC, which supports like a large amount of memory. So with 32 bits, you could only address like 4 gigabytes of memory, right? But like 20 years ago, let's say, right? It's around the time when a lot of systems started to support more memory, but we still had 32-bit CPUs. So how can you address more than 32-bit memory? So the CPU had the support to address more than 32 bits on the physical size, but you're still working with the same ISA, so the programs are still addressing 32 bits, and now you have you need to build a way for that virtual memory to be translated into physical memory, physical address that is larger than 32 bits. Well, this is how Linux has done it, but not every code in the kernel supported to work with that kind of address space, right? So in, like, as I described, Linux had a linear mapping into the entire system, right? You cannot have that anymore. So if you had to allocate a page that was higher in the memory, the Linux kernel would not have a mapping. So user space could use it, but kernel space could not use it as easily. They had to use, I think the interface was kmap, kmap. So if you had a page that was in high memory inside a kernel, you had to use it. You had to temporarily map it and then unmap it. So you had a 32-bit virtual address that you could use to access it. So the memory allocation interface, you can say, I need a page that allows me to do DMA. So it needs to be below the 32-bit physical address space, because I'm going to give it to a device that can only address 32 bits. Or it needs to be in the 16 or 20-bit address space, because I'm going to deal with a very ancient hardware that can only address 20 bits. And then there is the DMA zone and DMA 32 zone. Or I accept to have memory in the high memory address space. So you could give like a flag to indicate that I accept a page in the high memory zone. So that's the reason why Linux had to build this concept of zones, because not every system could use any physical address. They needed to have an address in a specific zone. But like in the case of high memory, this is 20 years old, and these days it's hardly necessary. We don't see many systems these days with that configuration, right? So how the kernel code allocates memory? Most of the time, I think people who are familiar with writing kernel code are familiar with kmalloc. It's basically malloc, right? But in the kernel, you give it the size, but you give it a flag that one of the things that it does, it says which zone can you take memory from, like we described. I'm going to go deeper on that flag scenario, but now we're talking about the size. So malloc implementation that most people are familiar with, it's a dynamic allocation that traverses free lists and tries to find the best fit for the size they're trying to allocate. But once you free that memory, you start having what we call fragmentation, right? So one of the a very nice concept introduced it into operating systems early in the 80s or 90s was the slabs concept, where you had these pages that were dedicated for allocating a specific kind of object. So if that object had a fixed size, so you could allocate only from that page or those sets of pages, so you could reduce that fragmentation. So the kernel, Linux kernel, works with slabs. You have slabs dedicated to a specific object, but kmalloc, even if you give it an arbitrary size, it will round that size to the closest, largest order 2 size, and there's going to be a dedicated slab for that. So if you're allocating 28 bytes, there's going to be a kmalloc 32, which has a 32 bytes object, so you allocate from that. That reduces fragmentation. And the Linux implementation, the one that's mostly used, Linux used to have 3 different implementations. The traditional slab, and then they added the slub implementation, which is more scalable, so it works more nicely on larger systems. And it uses per CPU structures, so you do not have to block when you try to access a slab that has a lot of contention, a lot of CPUs trying to allocate from the same slab. You don't have to wait and lock. You can have per CPU structures to allocate. Then there was a slob, which was more dedicated to embedded systems. It had more fragmentation because it was built into a more traditional allocation scenario, but it allowed you to use the same API over that different implementation. But the community has decided that those different implementations introduce more maintenance, so they decided to dedicate only to slub, and the older implementations have been removed. But when you do not have more free slabs or slabs with free objects, you need to now allocate pages to allow you to allocate those objects, right? So you start empty and you need to allocate a page. And when all the objects on that page have been allocated, you need to allocate a new page, right? And many other different allocations inside a kernel use those page allocators directly. So we have the API, the main API inside a kernel, which is get free pages. So get free pages, instead of receiving a size, it receives an order. So it's an order of allocation. So it's an order of 2 magnitudes. So 0 order is 1 single page. 1 order are 2 pages. 2 order are 4 pages. And so we have order 2 magnitude. And in order to support that, one of the systems behind it is the buddy system allocator. It's one allocation implementation that's very traditional, and it has been shown to avoid the external fragmentation. So when you put these slabs, which reduces the internal fragmentation on top of the buddy system, which reduces external fragmentation, you have the best of both worlds. Of course, once you have a system with many allocations that's under memory pressure, defragmentation is unavoidable and it happens. So you start to have to do something in order to solve this problem. One of the things that the kernel does is compaction. I'm not going to go through a lot of the compaction work here, but essentially the kernel starts moving pages around so it can release more higher order pages to the system. And then we get to the GFP flags, right? So the GFP comes from get free pages function name, right? That's why they call GFP. In the beginning, the kernel only had like 4 or 5 flags, and they were talking more about the context of the allocation. And then the allocator would simply say, okay, is this an atomic allocation? Then I cannot do these. If this is a kernel allocation, then I can reclaim memory, for example. If this is a buffer allocation, then I cannot use these kind of paths inside the allocator to avoid recursiveness and things like that, or deadlock, things that may happen. But today we still have the atomic and kernel. They were one of the very early flags that were used, but now they're built on top of more basic flags. So the GFP kernel, for example, it has the K-swap-G reclaim and direct reclaim, and the GFP atomic doesn't have those flags. So those are the real flags behind the allocator, telling the allocator you can wake up the K-swap-D to do memory reclaim. You can do a direct memory reclaim yourself, and we are going to talk quickly about these later on. But one of the things that we learned very early when we were working with the kernel is that if you're in a what we call a user context or a sleepable context, you can use a GFP kernel. If not, you're supposed to use GFP atomic. But that's not the entire story. Like, we also have GFP no IO and GFP no FS. So basically, if you're a file system and you're trying to allocate memory, one of the things that the allocator may do is ask the file system to save one of the pages into the file so it can release memory. But if it does that, then it's calling the file system again, and the file system needs to allocate memory, right? So one of the things that you do is that you give the extra GFP no FS flag saying, hey, you cannot call a file system function in order to satisfy me the allocation, right? And same for some of the IO paths. So you want to avoid them and avoid those that recursiveness. These days, the kernel has moved on to what they call context setting. So instead of giving those flags, you tell the kernel, I'm going to a file system context. So you save a flag, and whenever any function that you call tries to allocate memory, the kernel restores that context and knows that, hey, I cannot allocate from the file system. So it basically adds the flag for you. So you do not have to know that you're on the path of the file system. So the file system may call different functions that are going to call the allocator, and they do not have to give the GFP flag. So because before those things were introduced, whenever you had a function that could allocate memory, you needed to give it the GFP flags. So we had like that cascade of functions giving the GFP flags around and around. Okay, so so those two flags here, they can be masked off as well. So you can call get free pages, or even kmalloc, which is going to eventually call get free pages, GFP kernel, or not, and mask off kswapd reclaim because you don't want it to wake up the kswapd, for example. Okay, so when you try to get the pages, the kernel have a cache of pages. They have like a per CPU cache. It's called PCP. So the first thing it's going to try to do is get into that PCP cache of pages that it's per CPU, right? But first, the kernel is going to do some checks. And one of those checks is there enough free memory to give to whoever's trying to allocate memory? And, well, we could say that, okay, if there's zero memory free, then the answer is no, right? But if there's any single free page, you could simply give it to whoever's trying to allocate memory, right? Well, if you do that, and then you're going to have zero free pages. And eventually something is going to try to allocate pages, and that something is more important than the page that you have just given away. So it could be an essential driver to the system. It could be I/O. So if you need to free pages, you need to do I/O. And if you want to do I/O, you need to have free pages, right? So the kernel sets up the minimal free. There's a sys control, so you can tell the kernel, this is the minimal free bytes that I want the system to have. And the allocator will put a lot of effort in trying to guarantee that that memories, there's always that amount of memory free, right? And the kernel sets up also from that setting the low threshold, which is higher than the minimal, and a high threshold that is a little bit also higher than the low threshold. So the kernel does not allow the system to go into the minimal, because once you go into the low threshold, it already starts to release memory until you go to the high threshold. So the kernel doesn't even allow you to reach to the minimal very easily, right? So when you're trying to allocate and you're using like a GFP kernel, if you don't have free pages above the low threshold, the kernel will start to reclaim, right? So if you have given the direct reclaim flag, it's going to try to release memory in the same context as the process. So the process is going to sleep and have to wait for memory to be free. In the case of direct reclaim, the kernel only tries to release a very small amount of memory. But if you have added the kswapd reclaim flag, which, as I said, is already included on GFP kernel, it also wakes up a separate thread which is going to try to reclaim memory on its own, not blocking your process to allocate memory until it gets to the high threshold. So the kernel tries to keep that balance between the low and high threshold, at least, right? So why is there a low threshold and a minimal threshold then? Because when you're doing a GFP atomic allocation, or when you give like another flag, like GFP no fail, the kernel, now okay, I cannot fail memory allocation anymore, now I need to go into, but I'm below the low threshold, or very close to the low threshold. If I give these memory, I'm going to be below the low threshold. But they asked me to not fail the allocation, so okay, I'm going to go through my reserves. So this is what the kernel calls reserve. So depending on the flags that you give, one of those is GFP high. So GFP high is one of those that allow you to go into those reserves. And GFP high, surprise, is on GFP atomic. So when you give GFP atomic, you're already implying GFP high going to reserves, right? But you could use GFP kernel, add the flag GFP high, and still go through the reserves. Well, there are a lot of ways to work around, oh, I want memory very hard, but I'm in kernel context, I don't want to sleep, or I'm allowed to sleep, I can use a directory claim and things like that. So for example, when you're inside the network code uses GFP kernel, but it masks off directory claim because it doesn't want to sleep. It allows the kswapd to go into reclaim mode, but since that's a separate thread, it's not going to wait for the allocation. So in that case, the allocator understands, hey, I cannot go into directory claim. If I don't want to fail, I need to try harder, so I can go into reserve. So that's one of the other cases where you can go below the low threshold, even inside a GFP kernel. No GFP high is that if you mask off directory claim, right? So other flags, this is not the complete set of flags, there are other flags, but those are the ones that I thought were worth mentioning. So the GFP man-alloc and no man-alloc, they are opposites. They basically imply going to the reserves or not going to the reserves. GFP no retry is about if the allocation is very large and you need to do compaction and you cannot do compaction in case you need to sleep, right? If you cannot do compaction, it's not going to reclaim. It's not going to a loop trying to allocate memory. Retry may fail, it retries harder, but one of the things that it doesn't do is that it doesn't trigger the out of memory system. So one of the things that the kernel does is that once it cannot reclaim sufficient memory, it decides to kill a process. When it goes out of memory, okay, the only thing I can do now to release memory is kill a process. So it's the out of memory killer. So the retry may fail, it retries harder to allocate memory, but it doesn't trigger the out of memory killer, right? The no fail, well, if you cannot allocate memory and you have given the no fail, the kernel is going to panic, right? So it's no fail, but if it fails, it's going to fail drastically, right? Basically, it says, I cannot handle allocation failures by myself, right? Basically, it's the code that uses GFP no fail. It's telling the kernel, there is no way I can get out of the situation if I don't have sufficient memory. So it tells more about the code doing the allocation than the allocator itself, right? And GFP no warns that there are cases when the kernel cannot allocate memory, it's going to show a warning. But let's say that I can deal with allocation failures, and even if an allocation fails here, I don't even want you to show a warning. It's all fine and can deal with that myself, trigger a warning by myself, or I'm expecting things that might fail, so it's all fine to not show a warning. Okay, so let's move to a different kind of topic here. Don't have much time, but let's talk about user space, right? So we have been talking about the kernel memory, its labs, kmalloc, but I didn't show you one of the flags here, the GFP flags is GFP user. So whenever user space needs memory, instead of GFP kernel, we use GFP user. Well, that allows, for example, that you use high memory. It's one of the cases. It allows the system to sleep. There's no problem. But that memory is going to be mapped into user space. And there are essentially two kinds of memories that user space may use. One is the file system memory, so you can map a file. So you have an executable, that executable needs to go into memory, right? So the code is executed, it's mapped into user space. User space tries to access that, or you want to access data, you can also use mmap system call, so you can map a file, right? But even if you're reading a file, when you read a file on the file system, it may want to cache that file so it doesn't need to go to disk all the time, right? And what it does, it uses what we call the page cache. So it introduces, it loads the file from the disk, right? Puts that on a page, adds that page to a page cache. So the next time a different process tries to read that same file, it's simply going to read from that page. Doesn't need to go to disk anymore, right? So those pages get added to the page cache, and that takes memory. One of the other things that a process may do is call a malloc, which is going to call a mmap with no file descriptor. So there is no file that's being mapped. That tells the kernel, hey, you need to allocate memory, but there is no file attached, nothing you can read from the disk. That's what we call the anonymous, because they don't have name, they don't have a file associated with them. And when you're using a TMPFS or shared memory, those are anonymous memories too. So even if you're using a file system, in the special case of TMPFS or shared memory, they are what we call anonymous. They don't have where to go to disk, right? So why am I talking about this? Because when you're doing memory reclaim, you need to free memory. You cannot simply go and say, hey, this process is using this memory, let me just take it out of memory, and whenever it needs it again, oops, right? Your data is gone, here's a zeroed page, a free page again. No, you cannot do that, right? So what you need to do is you need to save that data somewhere. If it's already on the disk because it's coming from the file system, you can simply give it back to the file system if it has been written to. So if you have just read the data, not written anything, you can simply throw it away, right? So, and that's what the system does. When it collects the pages that it wants to release, it does a lot of checks. Is this from a file system, and is it clean? Just drop it, right? Is it dirty, but it's from a file system? Tell the file system to write it, and when the file system is done, then I can release the memory. That's what we call the write back. Oh, it's anonymous. There is no file system. What can I do here, right? Well, I need to go to swap. So that's why we have the swap space. So it has a dedicated space on disk where it can write to, or oh, this page is M-locked. Oh, it cannot go out of memory ever. It cannot go to swap, not go to the file system again. It needs to stay here, cannot do anything with it. Move on to the next page. So that's the difference. When you have, and so even when you have files on the page cache, you need to start releasing them. But how do you pick which pages to release, right? And there's this concept of working sets, that you have the memory that the process needs to access to do its work. It's called its working set, but any other memory could go out of the system into the disk, for example. But how do you decide which memory is being used and which memory is not? So basically we have this concept of least recently used, and the Linux have, classically it has had like these two levels of lists. It's the active and inactive. So basically any pages they are being accessed are in the active list, and once in a while the kernel scans the active list to find anything that has not been accessed for very long and moves it to inactive. And when it really needs to release memory, it goes through the inactive list, and those pages are the ones it tries to release first, right? So they even have like what we call the shrink inactive list. Is the function that goes through the inactive list and tries to release those pages, while the shrink active list tries to move pages from active to inactive. That's what kswapd tries to do all the time. But pages can be moved to the inactive to the active list when they have been recently accessed. And there are a lot of heuristics to try to find out which ones are active and which ones are not. There's the concept that's called the refault. So when you move something from active to inactive, you unmap it from the page table. So you're going to have a page fault when the user space tries to access that page. And then you have a signal, hey, this is not really inactive, I need to move it back to active. And you even move it to the head of the list. So and there are other heuristics that tell, hey, there's been a lot of refaults here, so maybe I should not be moving these to the inactive list. A real quick bit of history that I have gone through here is that since the early days of Linux until around 2001, these pages, they had an age. So they were moving to the active or inactive list according to an age that the kernel assigned to them. And there are a lot of heuristics in order to assign them. But they decided that, not they, well, I think that Andrea Congelli was working on the VM and came up with a different code, and it was applied on a stable kernel, so a lot of people were not happy about that happening in a stable kernel, but that happened. And since then, the kernel has not have any ages for the pages, right? And around 2002, or since the early days until 2002, the kernel, it needs to unmap from the page tables for all the process a given page that's going out to swap. Because if it doesn't do it, when the process tries to access that memory, the CPU is going to access it. And that was moved to what we call a reverse mapping around 2002. And funny thing is that now we have the multi-generation LRU, which has introduced ages for the pages, and it has introduced the page table traversal, all the things that were removed back in 2001 and 2002. So things have come around, and now we're doing a more complicated version of what we used to do before 2001. This has been a recent, relatively recent introduction to the Linux kernel. My time is out. Any questions?
I have a more of
Question for, oh, sorry.
I have a more philosophical question, if you allow me. Is the Linux kernel somehow finds a way to serve memory in many different devices with many different hardware architectures, ways of accessing memory directly, MMA, NUMA, all those kinds of devices we have out there. In your opinion, what is the architectural secret that allows the kernel to be usable in such a wide range of devices?
Evolution. Because when you go through to the 1.2 kernel code, it didn't support SMP. 2.0 supports SMP, has no idea what NUMA is about. So it's all and I think that also the contribution and collaboration with many people coming from those different scenarios. And I want the Linux kernel to work for me on an embedded system. I want the Linux kernel to work for me on a NUMA very large server system. And people are trying to collaborate and trying to come up with solutions for their problems. But at the same time, there are people who are maintaining that code and trying to come up with the best solution that at the same time solves a problem for a new user, but continues to serve its previous users, right? And that has only come with a lot of time, a lot of people writing a lot of code. So if you go back 25 years ago, there's a lot of things that didn't work on the kernel was not fit for. So I would say that that's why it works.
All right, thank you, Pascal.
Ah, daqui da sala, né? Tá bom.
Pessoal,
Puxar aqui, né? Tem que pegar. Tem um antigo, né? Ah, é bom, né? Eu amo. Posso bloquear aqui?
Pode deixar aberto. Obrigado.
Tá. Ah, o HDMI. Já estou fazendo
Só alguém conhece o Carlos Nihilton? Ah, é você.
Então, cara, Léo.
Acho que eu botei sua foto errada. Tá certo?
Oi. Tá bom, tá bom.
Já tá aparecendo.
Tá aparecendo? Tá bom, então. Okay. Hi everybody. Thanks for having me here in FOSForums. I'm glad to present here. I like this conference. Not speaking more. Yeah, but Leo told me that there are some microphones capturing, but they are complaining it's low.
Sorry?
They are complaining it's kind of low. They can't hear me. Okay, I'll try.
The problem is that the microphone is too low.
Okay. Yeah, no, let's try this way. I'll try to speak a bit louder. Let's see. Okay, so I'm Guilherme. Most of you, probably 97%, know me. So I'll be brief in the introduction here, kind of short bio. I studied in Unicamp in the past. Then I moved to IBM, working in Power I/O team on Linux Technology Center, doing PowerPC hardware. Then Canonical, working with customer support on kernel, etc. And now I work at Tigalia, which is quite a nice place to be. It's a worker-owned cooperative, doing mostly free and open source software, and it's quite great, right? So both are available for compatibility, etc. The preferred way is kernel tracing, right? There are many front ends. People like them, like they are terminal based or UIs. I'm showing here the like manipulating the files. It's in the sysfs, right? The output of the trace data is on a ring buffer in the trace, like sys kernel tracing trace. It's dynamically produced log, so it's not like as you're collecting functions, like one function in the tracing. It's not that's writing there. It's just marking some structures, and when you dump this tracing log, it's constructed on the time of the output. So we start. There are some comments here how we started tracing, etc. Let's start with the demo, right? So one of the reasons I asked Leo to present here in my own laptop and here manipulating is because I'm running a VM. So it's easy. It would be difficult to do in another computer. I need my own setup, right? So let's start by showing how tracing works here. So basically, we are enabling, the demo is a kind of pre-recorded in form of scripts to make my life easier. So I just run scripts, it shows on the screen, it should work, right? So here we enable that, and let's see the outputs, right? So I enter syskernel tracing, so showing the trace log. Easy, right? So it's big, it's massive. So, but let's talk about the outputs. Then we are talking about filtering, because it does not make much sense to show all the functions, right? That are running. So the output works in this way. The first part is the process. So this is the cat process, right? The PID is 790. Then the CPU in which it's running. Then there are some flags here, like flags of the state of the scheduler, if it's interrupt context, things like that. We have 5 flags here. Then the timestamp, and then the function name and the color, right? So the last one here is DL server update, called by update curve, right? So now let's get back to the script, right? So we clean up here and move on the presentation. So it's massive output, right? So it does not make sense to use that. What we want is some filtering, right? So we can restrict by PID that we want to investigate. The buffer is mixed between all CPUs. We can restrict by CPU we want to show, right? So, and we need an example here to show things. So I'll use NVMe clip. Basically, is the tool for interacting with NVMe drives. I have a virtual NVMe in this virtual machine here. So it's a virtual drive by QEMU attached to the VM, and I can use this tool to send commands to the storage and show what happens in trace, right? So we can restrict by functions, which is very interesting. We can do echo regex to the setf trace filter. We can also use modules to do that, restricted by module, using the mod modifier here. We can check the available functions that you can choose in the available filter functions, right? And we can disable. Imagine I want to enable all the functions in the NVMe driver, but 1 or 2 functions run a lot. So I want to exclude them to not pollute my output. I can do that. So enable all NVMe driver and then exclude some functions, right? So let's see the demo here. It's a slide 4. So we are filtering only the NVMe, right? So let's see the outputs. Trace filter. See, only NVMe functions. So we are restricted to that. It's equivalent to do this another thing. It's more proper to do because I'm using the module modifier. So I'm saying to the kernel to put all functions that are on the NVMe module. The other one was by name. So we have functions that are not like, let me show here, that are not named NVMe in the module. Like, I guess the third one, HMB store, right? So it was not caught in the first one. And we can filter out functions, right? So NVMe init queue. So if I grab here, what was the name of the function again? Init queue, right? So init queue. It's here, right? And then I run a command to remove it with the negation here, which is exclamation. And it's not anymore. Right, so now I ran this command, which is the ID control. Basically, it will ask the device about information of the drive, etc. Let's see the output, how it is. Right, it makes sense now. It's not massive or huge. You can see what happened, right? Start with that open, etc. And okay, let's continue the demo. So I have always a cleanup in the end of the thing.
Right, so more about filtering. We can show, interesting one, we can show stack traces of the executed functions, right? And we can use markers. Markers are useful if you if you're running tracing from a script, you can start, you can mention to the dev trace that you're starting in that point, but basically by writing a string to the trace ring buffer. And you can also adjust the size of the ring buffer because eventually you want to trace a lot, so you increase that. Okay, let's dig a bit. So it's C. So now we are filtering only one function, which is setup command, but showing the stack trace, right? And I'm using markers. Let's see how it outputs there. Oops. Let me clear this one. Okay. So see, we have the marker here. I call command started. Then the function that I wanted to specifically filter for that, and if you miss that command. Then I stack trace of the function, and then the final marker, command finished. So it helps to organize the trace output, etc. One thing I like about F-tracing is the profiling capabilities, like counting the number of the functions that were called, the average time of them, etc. That they consume, right? They run in how much time. So let's do it here now. So basically, I disable the stack trace to not pollute, and to enable that, you echo here to function profile enable. But notice that it depends on one kernel config function profiler. I guess it was off in Debian, because when I was trying this example at my house, it failed. And then I was, why it failed? And I checked, it was not there. So I rebuilt the kernel with this one, with this function profiler. So maybe has some overheads and it's disabled by default, right? Then what I did here was run 3 times the same command, but I forced it to run on CPU2 with task set because the profiling shows data per CPU. So to help the output, I just forced on CPU2. That, of course, if you are doing real case, you can check all the CPUs and do some statistics with all of them. But just to easy our life here, I just set to CPU2, right? So let's see the output. The output is in trace stat, right? Trace stat function 2. Name is a bit counterintuitive, right? It's trace stat function the CPU number. What is function 2? You can call it the second function I'm tracing. No, it's the functions on the CPU 2. So since we restricted to NVMe setup command, okay, it shows that the function ran 3 times, and time it took on average is 5.5 microseconds. So if you have one outlier, it might, you can get it here in principle because of the deviation, but there are better things to check the outliers. I'll show here now. Okay. The graph tracing. So, as I said, ftrace basically instruments the first instruction of a function. So it's an op, it's changed to if you enable tracing. Now the function graph tracing is a bit more complex because it instruments the enter points and the exit points of the function. So it's able to build call graphs. Visually is way more funny to see. You can see everything that's going on, all the functions called that was subcalled by a routine, right? And it's pretty useful for tracking the time executions for the functions. So the idea is to change the tracer to function graph. You have the same filtering. You can filter by CPU, by PIDs, etc. Function name, of course. And I'm using a special one here that I like, which is the fun graph tail. Basically, in the output, you have opening brackets when it starts and closing brackets. So you put the name of the function also in the closing brackets. Helps a lot to see. And to track the time executed, there are some eye catchers. If the function takes a lot, you have these markers here. A lot of time, like 1 second, which is big in the kernel realm. So you see the sign, the money sign, dollar sign, right? And okay, let's see the demo. It's 5, right? 5, okay. So I named the things about based on slides. Okay, so I enable the graph 1 and filter to show dev ioctal, NVMe dev ioctal. Tracing on, I enable this option, so let's run the command and see the outputs. Output is big here, a bit bigger. So let me navigate a bit here. To the beginning. It's quite big, right? See, it starts with an NVMe ioctal on the model NVMe core. It opens the brackets here, then calls the user command, then see, NVMe command allowed. This function executed and finished. That didn't call any other one. Then submit user command. There, it's the whole set of functions that submit user command called, like the block ones, etc. And you see here in the left the time took by the functions with the markers. So in the end, if you go way down, we see dev ioctal finished in 500 microseconds, and you see the whole path of execution of it, right? Let me clear here and get back to the demo. Now there's a hack here. I want to show the eye catchers here and why it could be useful to debug like slowness in some function. So I hacked the model to delay in the beginning of the function. So it will show there like the delay. Let's see. To do that, I built a model here using the K-probes technology. Technology, but fancy, right? Okay, the K-probes infrastructure in the kernel. So I will talk a bit about K-probes later here. It's quite powerful. It requires a bit of assembly knowledge but it's quite nice and useful, as we can see here. So I ran this model, right? Now I will run the same command again, the ID control. But notice that it will take some more time. See, between the ID control and the read, it took 1 second that I asked it to do hacking the model. So the output now, trace. See, last line, it took 1.5, basically 1 second more than I have 10 minutes. Okay. See the $ here, and if we check the execution, we'll see here my delay. Where's my delay? Okay, should be here. I want to show you. Okay, it's here. Oh no. Oh, it's here. It's a matter that we just need to. Okay, found. We just need to find it. See, delay here in the line with the. I don't know how to say this hash thing. The eye catcher here. Let me put in the first line. So see, one second delay here. It's introduced by my model. We can see even that here in the K-probe ftrace handler. So it's run by my model. My model introduced this delay. So we can use that to debug the times if it's taking too much, right? So clear again. I'm finishing in 10 minutes or 8 minutes. Okay, I remove the model, clean up. Now let's talk a bit about another kind of tracing, which is the trace events. So ftrace, recap. Ftrace, you have the function, and you can instrument in the beginning by changing the knob and see the function execution. Function graph, you can instrument the entry points, exit points, call graphs. Now, static trace points. Basically, if a kernel developer feels that some information is interesting to have there for debugging purposes, etc., it can add this static coded trace points that you can enable, disable. So the principle of the overhead or of enabling, disabling is the same of ftrace. Low overhead. If disable, no overhead, but if you enable that, it's low. But then they are static coded and can show the information that the person writing that code wanted to show, right? You have a list of events here. I think it's interesting to show this list because it's quite, let's see, events. No, I'm wrong term. It's here, events, right? So it's per subsystem. See, you have DMA, you have ext4, with trace points for the file system. We have syscalls, all syscalls entering exit points, architecture stuff, KVM. So let's see, for example, in ext4, right? the developers of this file system wanted to have all those trace points, so you can enable and see what's going on in that path. The information depends on the trace point, of course, personally group. So see here, write pages. So if we got format, see, this is kind of the output the person wanted to show is a structure here, right? You can show the page skip, the range start, etc. So the person writing that judged that it was interesting to see here. So let's have one example here. Okay, it's 6. B6. Right. Okay, so I'm setting the not tracer because I don't want to pollute that with that trace. And then I am setting the sys enter ioctal and exit ioctal. So it's a syscall and the enter and exit of that. Run my command and disable the logs. Let's see if it collected. Okay, it's here. The thing is, we show 3 because there are some serial ones like TC gets, TC sets, the other ones. But the main one that is important for us, I wanted to show, is the first one. See, the command is a bit big. You have like the file descriptor, you have the command, which is important, the argument of the ioctal. The first one is the NVMe admin command. So if you're debugging NVMe, you want to see this IOCTL happening, here, it's here, right? So let's continue here. And then I guess last one, kprobes. So kprobes is kind of the events we just talked about, the static ones, but dynamic ones. You can do whatever you want basically by writing to some file here in the trace subsystem. The semantics, you have a probe name, you have the function that you want to probe, the offset, and what you want to probe. So what can you probe? You can probe, for example, arguments, return values, or anything in the body of the function. But for that, you need to check the assembly to see the offset you want. So you can match like a register value, you can match like a variable, in that point what happens. The easy one is to show the beginning and the end, right? So you have two kind of probes. The ret probe for the return value and the regular probe. If you probe on the offset 0, you are probing the entry of the function. So you can get the arguments, right? So to check the arguments, we need to know the ABI we are talking about. Here x86, so the parameters are passed up to 6 parameters in the registers, the I, SI, the X, in that order. So I put a probe here again in NVMe dev ioctal, right? So see the syntax here. The ret one is easy. You just put the name of the function, the ret vol, and the type of the return. But the other one, command name, I call command NVMe, right, is in the beginning of the function, and is SI because I want to show the second parameter. And it's an hexadecimal, 32 bits. So let's see the example. 7, right? 2. Okay. Clean up again, up. So add in the kprobe events, right? One, then the other. Notice it if you add more, 5 minutes, fine. If I add more, I need to change here the signal, or else I'll overwrite the first one. Then I enable that. I can enable them individually, or I can enable all of them. All the kprobe events is the equivalent. Run the command. Let's see the output. Clear. Oh no, I'm not clear. Just so we can compare with the other one. It's interesting to compare. Okay. So see, NVMe dev ioctal was called with the command. It's the same command as in the previous output, right? The previous one is the one that somebody wrote in the system called ioctal. It's a static event, but the other mine is the kprobe. So it shows the same argument, of course. We expected that, and the return is the same. We can see return 0 is the second line on above. So 2 ways of getting the same data, but notice kprobe is completely customizable. You can do in any function you want, right? Okay, Then we clear the events, and then I guess that's it about the examples. Then some advanced topics not covered, right? F-trace instances, for example. If you want to debug, use the trace buffer to debug two areas, but you don't want one area to pollute the other. You create instances, which is super simple. Basically, you go to the instance folder and create a directory there. Each directory in this instance folder is one full tracing system. So you can trace like DRM, and in the other directory trace ext4. They don't mix. It's great for parsing the logs, etc. Then you have more advanced tracers like HWLAT tracer, which can get some hardware latency things. So it's useful for debug SMIs, which are interrupts from the BIOS, the firmware. So if the firmware is behaving badly, you can maybe get here. MMIO tracing, super nice. It's a feature to debug in MMIO access to devices. Very useful for reverse engineering, like a GPU. Then we have kprobe, and you probe full events, full power, as I said. Basically, you can probe an instruction, just study the assembly, the offset, and go nuts. And then you have the kprobe modules that I use to instrument here. It's a module that will do the probe. But why use a module? Because then you can run code. You can probe one instruction and add code to run there. You can change the path. You can change an if to check, etc. And there is a BPF which is very trendy, but I never worked with that, to be fair. I use it tracing, etc. I'm old school, let's say. So I need to study more BPF, but it's quite powerful and trendy. And okay, that's it. That's the references, some interesting guides, and thanks for the attention. If you have questions.
There's one question. Is an invitation, Professor Guilherme, as we're sitting there. So we are starting instrumentation trace test group with FOSForums. So if you want to join, educate them about what they need to do and work with them.
Thank you. Yes, it's interesting. We can talk later, by the way.
Igal is a member, so you can join anytime.
Yeah, of course. Yeah, cool. Thank you, Sandy. Nice. Okay, I guess that's it. Thanks, guys.
Thank you.
Alright, here we are. I hope you don't call me a traitor for using Windows in a free software conference.
You're not sure.
Sure.
You're sharing, but it's not coming.
Let me try again. Oh, keeps dropping connection.
You're not the traitor because now Linus and Bill Gates, they have dinner together. So
Feel better about it now that they are dinnering together, because a few years ago I think there was a comment. I'm not entirely sure. I think it was with Ronix. There was some guy who made a post about WSL and how Linux and Windows play together, and there was a comment saying something like, "Oh, those traitors helping the devil," something like that. That was heartbreaking. Not nice to be called like that. So, welcome. I doubt you know me. It's my first time in this conference, and although I studied here in Unicamp, it was during the pandemic days, so I didn't frequent any of those places. So, for all the matters, my first time here. Thank you for accepting my proposal. And let's talk about this cheating, maybe? Traitorship? I don't know. Ubuntu on WSL, the Windows subsystem for Linux. But before that, let me introduce myself. My name is Carlos Nielton. I'm a software engineer at Canonical, more specifically on the WSL team. We have a team dedicated to WSL, so it shows that this platform has some importance. And I'm also a Ubuntu member, not a developer just yet, just a regular member. I have the right to vote, can share stuff on our discourse. I'm also a free and open source software enthusiast for ages. Kind of shy, but always playing with tools, trying learning. And as I said, a former student of Unicamp in the software engineering specialization course I took during the pandemic days. And father of 3 little cute boys that drive me crazy, but I love them. It is what it is. So here we are to talk about this strange association between Windows and Linux. Not long ago, lots of you guys may have good memories of these times when we would put a red cross like that in the middle of those two guys, like enemies fighting like hell, and you couldn't imagine a scene like Linus Torvalds having dinner with Bill Gates. It's strange times we live nowadays, I'd say, but at the same time, it's a great time to be alive and be engaged in open source communities and working with open source. Because we see that after years of battle, we would say, open source won. That's the truth. So nowadays, the big techs are all built on top of open source tools. Even Microsoft, though they were against in the beginning, nowadays they are pushing more and more for open source adoption. Their foundations, their infrastructure relies a lot on open source technology. All this hype of AI that we talk about every day, it's mostly built on top of open source. So it's true, we won. So this association no longer applies the red cross anymore. It's more like a blending. Some of you may remember this documentary, Revolution OS. I think it was revolutionary for me when I first watched it. I was just learning about Linux and all of that, and I saw this, and this completely made my mind about the idea of freedom of software and seeing how passionate the founders of the free software movement and open source software movement were influenced me quite a lot. Nowadays, especially for the younger generations, seeing this kind of passion and the feeling of battle that they were fighting seems a bit too extreme, because younger generations live in this world where open source is ubiquitous. Android is probably the most popular computing platform, and it's almost entirely made of open source. So it's hard to think that way, but it's good to remember the history where we come from, so we don't take the risk to repeat those dark days of fighting and whatnot. So after I said that, let's get into the main topic, which is the Windows subsystem for Linux. What that is, according to Microsoft documentation, is a feature of Windows, the operating system, that allows users to run a Linux environment without the hassle of managing a virtual machine. Linux users, especially those running desktops and doing low-level tests, playing with kernel, testing new releases, are pretty familiar with setting up VMs with QEMU, or maybe a higher level tool like libvirt or maybe VirtualBox, I don't know. But for Windows, it's quite hard. I mean, traditionally you had the option of Hyper-V, which has facilities for management, but that would come with a cost of a Windows Pro license. Or you would try to resort to tools like VMware and VirtualBox and pray for the best, because sometimes they don't quite do what you want, or it's kind of hard to set up the networking or passing through GPU, the kind of advanced work that you could want to do, and the tool kind of restrict yourself in that sense. So the WSL comes as a solution for users that for some reason need to stay on Windows, but at the same time needs to interact with Linux in some sort, either for developing a cross-platform tool, or because they are creating some web application that will be eventually deployed on a cloud, and that's mostly a Linux server. So those are the audiences of the WSL system. And when I planned this talk, I thought that we would be like lots of students, young people. So I put this chart with the intention of scaring them and skipping it away, even because I had tons of slides and demos to show, so I'm not sure if we can dive too much deep. But since I see that you guys are pretty advanced, I can give you kind of a glance of what's going on with the WSL. So we have the Windows side, which is a bunch of services. I mean, executables talking to a common service. And this service handles a virtualized socket that communicates with the Linux world. We won't talk about the legacy architecture of the WSL. We'll focus on the WSL 2, which is built as a virtual machine. So it relies on the facilities that Windows brings for virtualization, the Hyper-V. But to make the WSL popular, they had to rethink how Hyper-V was distributed. So nowadays, if you buy a Windows Home laptop, you get some of the Hyper-V APIs available, and you get the WSL already. So any entry-level laptop offers you the possibility of running Linux workloads with ease. And internally, this Linux box is a very optimized virtual machine. There is a custom init system, they call mini init. It manages the virtualization part, but also some integration services. We're going to talk a little bit more about what integration is in this regard. But for the Linux user, as well as for the Linux distribution targeting the WSL, we live in this box. We don't kind of see the magic that sets up the environment where we are mounted in. We only see that there is some init process that calls our init process, in Ubuntu's case, system D, and there is some kind of a Plan 9 file server that we don't mount. It's injected by this machinery around our little box. And there is the session leader, which is the process that is created when the user interacts with the WSL for some reason. It could be a script that the user is running, but most often it's a shell. It's bash, CSH, whatever you run as your shell. On the Windows side, there is this component object model APIs that those binaries call to this WSL service.exe, which is the main component of the WSL machinery. WSL.exe is the entry point when we invoke a command inside the Linux box, or when we start a shell, we usually go through it. But there is broader, the graphics guide, WSL-G, which allows running graphical applications. There is the WSL config that manages configuration, and this DLL is an API because in the early days, and until not very far ago, the main way to distributing the WSL was through Windows executables. That changed recently in 2025. Microsoft announced a simpler format. So distributions only care about creating a root file system with a little bit of a meta information about what's being shipped, and we no longer need those Windows binaries anymore. Yeah, let's not dive too much deep. I know that you understand more than I probably do about CNIT system interactions and whatnot. But the message I want to share here is, this is just one more platform. Linux runs on mobile phones, on cars, on cameras, on satellites, on personal computers of all file formats. So, for us, Windows is just one more platform. As you target a cloud infrastructure, like you would probably create a cloud-optimized image for deploying on AWS, or Google Cloud, or Azure, we also create an optimized image to deploy on Windows. Like Windows is a target, in that sense. And ultimately, the WSL is the best feature that Windows ever created. Let's be frank. Ever since Windows guys adopted the idea of this tool, they revamped their developer story. Because you have two kinds of developers on Windows. Those guys that run Visual Studio and they are creating Windows-specific applications, and those that are most often targeting cloud deployments, but happens to have to be in a Windows box because that's what IT requires, because that's what their management solutions are for, that's what their compliance restrictions require. So they have to deal with this crossing of both worlds. So for those guys, after the WSL, Windows became a much more usable platform. With the WSL, it came the Windows terminal. It's so much better than the original console host, the command prompt that everybody knows and hates. Even today, the com host was revamped. Even Notepad.exe, it's a completely different text editor nowadays. And it all started with the adoption of this tool. And I have the pleasure to say that now WSL is completely open source. It didn't used to be that case, although it was built on top of open source technologies like the Linux kernel itself. There was some components like the mini init that I showed, all those exe stuff that was happening in the top, and nowadays they are all open source, ever since May 2025. So I have a couple of demos to share with you, and the number 0 is this presentation. It is per se a demo. Let's see if I can show you. This is a browser session accessing localhost 8099. So there is some kind of web server going on. The web server itself, it's quite silly. It's just a single web page. I'm sure nobody would do this in real life, but I wanted to show off. So I have just a Python HTTP server serving a simple file, HTML, created from slides.adoc using ASCII-doc review.js, just because I could. And this is to demonstrate that one of the most useful features of the WSL, in my opinion, at least for web developers. You can spawn an instance of the WSL distro easily, and you can start developing your web service easily, and you start serving, and from the host side, you access it like it was being served on Windows through localhost. Any port that you choose, provided it's a high number port, you access it as if it was running in localhost without doing any configuration at all. So this is the value that the WSL brings to Windows users and Linux developers in general. this easy integration without configuration, zero touch. Just by deploying, you get this kind of feature for free. Take this out of the... So what is Ubuntu's role in this context? WSL, as I said, is a platform. They don't provide user space. What they bring is the virtual machine management through the part of the Hyper-V APIs that are exposed. They bring the host services, the integration on the host side, the Linux kernel. It requires some custom patches, but they are all, of course, all open source. There is a repository on GitHub where anyone can audit what is Microsoft changing in the Linux kernel. And some of those patches were even upstreamed already. There are also graphics and media stacks, so it's possible to run graphical applications, to listen to audio, see videos, do some crazy graphic stuff, because why not? And also, as I showed you in the box, there was some adjacent Linux components, the mini init, all the idea of a Plan 9 server, what we would call guest services, are part of this platform, but they don't come with user space. So that's where we jump in as a Linux distro and provide with all the binaries that compose the user space you would expect, from compilers, shell, binutils, to high-level applications, Node.js, whatever you want. And we're not alone. If you do WSL-list online, you're going to see a catalog of distros that are playing together with WSL. And the list is not very short. You have Alma, Debian, Fedora, SUSE, Ubuntu, Arch Linux, Kali. Number of popular distros out there, ready to try with zero touch, as I said. We work in Canonical to provide Ubuntu with some differentiators, I would say. Canonical is invested in WSL. Prove that we have a team, and I'm here talking to you about this. We pay attention to small details. Maybe advanced users wouldn't give a lot of value to those, but from the setup experience to the terminal appearance. And we try to keep the fidelity with that users would expect in an Ubuntu machine, in case you are used to deploy Ubuntu servers. You know what to expect. So we strive a lot to make sure that what we have in WSL is fitted into that experience. But at the same time, we try to cooperate and build on top of those features that WSL bring. For instance, not long ago, it wasn't possible to have systemd services running in a WSL instance. By default, WSL was made to be very simple, and they didn't rely on, nor even consider starting systemd. So we partnered with Microsoft and with the community. There was many demos published out there showing ways to start systemd in a confined namespace, so you would think it's PID1 and everything would just work. And that influenced the design that eventually Microsoft put together, and nowadays, systemd is there by default. It's still opt-in, but if you install Ubuntu, you get systemd already running, and you trust that services that you would expect your server to have would be there as well. When I say about the setup experience, here's another demo. I recorded because this would rely on internet. I couldn't take the risk. So here we download an image. It's like 300 something megabytes, and WSL is processing this image. It creates a virtual hard drive on Windows, ext4 formatted. And here's what I talk about setup experience. On Ubuntu, we do this trick of reading the Windows username and kind of pre-filling the prompt for creating the user. It's a small trick, a small detail. Most users wouldn't pay a lot of attention to, but it's one less point of friction that we try to make sure users won't have. And I was talking about the appearance and details. So if I show you, this is Windows Terminal. No, I don't want it. I hope you see Windows Terminal. If I start an instance of Ubuntu, Ubuntu users would immediately recognize the colors, the Ubuntu font. So this is kind of a detail that we try to pay attention to. During the first setup, there is a process where we find the proper location, and we drop this font and we register it in the Windows registry, and also we drop the terminal fragment referring to that font and color, so we preserve the branding. It's like an identity. If you ever see someone talking on the internet about, I don't know, Kubernetes, whatever, and they do a demo and you see those colors, you know they are running on top of Ubuntu. So this is, for us, it's important. Another thing that I would like to share with you is Cloud Init. People that work with cloud would know that, but it's not common for desktop users. It's a de facto standard for initializing cloud instances. There is a declarative way to say, create me this user, install those packages, update my package registries, and whatever. And we integrated that with WSL because we believe that users are constantly creating and destroying those WSL instances on their machine, mimicking some deployment that they have. They need to troubleshoot something, you implement a new feature on top. So having Cloud Init is a way to reduce further friction. They can just have a file describing what they are trying to set up, and the thing happens automatically. So for this demo, I'm showing you a small piece of a cloud config. This is the location where the user drops the file. Here's named Ubuntu because the instance I'm going to deploy is also called Ubuntu. It will set my locale to Portuguese Brazil. It would create me this particular user. It's going to write to this file, so the user that it creates, it's considered the default. We'll install those packages because I want, and we'll create a file. It's just so you have an idea of what Cloud Init can do. And here is the same contents that I was showing you, apply to the same location. Of course, the video is edited. This will take a bit longer in real life. But eventually, when the WSL starts this instance, it will find a script that's pre-configured, and it launches that script. That script is under our control. So in the case of Ubuntu, we noticed that there is a Cloud Init file at the location we expect, and we follow that. So you see ZSH being installed, the .ipso file was created, the GTK, for examples, package was installed. I can launch it. And you see it really looks like a GTK application because it is, and it's running inside the Linux box. And then Octavia, which is also another package that I mentioned in the Cloud Init file. So this in particular is one of my favorite, if not the favorite feature of the WSL. I constantly destroy the WSL instances and recreate them. Oh, really? I wanted to show a little bit more about Visual Studio Code as an example of an application that runs on Windows but takes advantage of the WSL and integrates in a nice way. You see that we are installing an extension inside the WSL, but this GUI is a Windows application. It's not like we're rendering it inside Linux. So the Visual Studio Code takes advantage of the WSL and distributes the workload. There is a GUI on Windows, there is the actual processing happening in the background. Here, we're installing the Flutter extension and the Flutter framework because eventually we want to try to develop something. And specifically about Flutter is a nice use case because Flutter can create applications that target mobile and desktops. So in the same machine, you can easily be working on your Windows and your Linux versions of your same application. And you can even go nuts. There is this idea of cross-OS interoperability. You can see each other's file system. You can invoke binaries of each other. So you can, for instance, have your Flutter application this is a Git repo, as usual. I won't demonstrate the whole workflow, but we have an application here that we could run. And at the same time, I also check it out here. And look at this. The remote for this Git repository is mntd counter. This mntd is a mount point that Windows creates by default for the WSL distro to be able to access Windows files. So I literally git clone mtd counter. So if I do something on the Windows side and commit, I can just git pull, and it's available inside the WSL, and then I can hot reload and do whatever I need to do on my application. So I can see two versions at the same time. I can put them in parallel, and I could go nuts. I could run rsync. So if I save, I would push to Linux and restart the application. This is all possible thanks to this idea of cross-file interoperability. It's possible to go even crazier, like this snippet, it's useful to create random passwords. You read some amount of bytes from you random and you base 64 to make sure it's this ASCII string, and you pipe to clip.exe. That's the Windows clipboard. So you don't even see the strings, you just Control V and it's in the application you want to drop it there. Just so you don't think I'm lying to you. Where's Notepad? This is what it generated. I can run it again. It generates me more stuff. So this is what we're talking about, cross-OS interoperability. And I didn't show you, but the way I invoked clip.exe, I could invoke any other Windows application, provided it's in path. And everything is a file. We used to say that in the Unix world. So if I come here, where is it? So let's say this. So this console session, this TTY, is connected to the device PTS0. So I could, for instance, explore. Let's see. It keeps opening on the main one. Let me show you since the beginning. From the Explorer, Windows Explorer, I can see my WSL instance file systems. I can navigate through them. I can find dev, PTS. So here's my device 0. I can probably open it with Notepad and say something. When I save it, of course it wants to save me a file, but if I go back to the WSL, so I wrote to the console. It's a very silly example that I stole from the WSL's product manager, Craig Lowen. But just to show that it's even an educational tool. If you want to understand how Linux works, you can still do it from the comfort of having a session, desktop session with all the graphics you need to please you. And a quick note on GPU pass-through, because I find this particularly complicated on other virtualization solutions. So there is a guide about deploying CUDA and other GPU accelerator frameworks. And I'm using CUDA in this example because this laptop has a modest NVIDIA GPU, but it's workable. So we need latest drivers from NVIDIA. It's quite a big of a driver set, but eventually we install them. And it's transparent to some extent the way the GPU is passed inside the WSL instance. The only thing that we need is to install the correct version of CUDA inside the WSL instance. The Windows side is solved, NVIDIA stuff is installed, so I go on the Ubuntu side. We have documentation for all of that. I'm too lazy to spell all of those words, but eventually we'll be installing CUDA, latest version. It's a lot to download. It's gigs and 3 gigs, I think. The video is a little bit speed up as you may guess, and it still takes a while. Should have cut even further. But yeah, eventually we're there. CUDA is installed. I can see the GPU from inside the WSL without doing any other thing. I didn't configure anything. I just made sure that CUDA is in my path and I'm compiling some CUDA sample application easily, without doing any magic. And I'm showing this silly example, but there is people doing serious stuff out there, training machine learning models, or at least testing machine model training workflows through the WSL because it's easier. That's all I had to share with you today. Thank you. If you have any questions.
I have one question. I never use it WSL at all. So is there a limitation the number of instances that I can have running at the same time?
The practical limitation is your CPU quota and memory. I mean, you can create as many as you want and you start running them, but there is a fixed amount of memory and CPU quotas that get assigned to the VM. So eventually you're gonna be lagging and the instances will start to drag.
Is this configurable? I can set?
Yes.
Okay. So if I want to run a Kubernetes cluster,
it's possible. Yeah. There's tons of people doing guides on how to deploy Kubernetes clusters or play with Docker. Docker is highly invested on the WSL. It's like, for them, it's the way to have Docker running on Windows.
So I have used it, but I have a question. It's not really for you, but the decision to have Plan 9 as the file system inside Linux is just so bad looking. I mean, is there any plans? Do you know if there are any plans to use something more modern and more maintained?
Well, Microsoft keep a fork of Plan 9 just because of the WSL.
Yeah, but I mean, Plan 9, at least in QEMU, Plan 9 has been its legacy for many, many years now. It's in life support. And, well, this is a personal history, right? I mean, when I moved to Linaro, I decided to use WSL. When I got my notebook, it had Windows installed. I said, I'll give it a try. But unfortunately, one of the very first tasks that I had at Linaro was to do the kernel. And it's so slow, but so slow. Plan 9 running, I mean, extended 4 and Plan 9, then WinFS. It's so slow. I mean, it took like 3 hours, and with Linux it was like 20 minutes. So I just quit it because of that.
You just shared the reason why Microsoft couldn't deprecate the WSL 1. I said that I wouldn't mention this, what we call like legacy architecture, but it's still out there. So when Microsoft first started the WSL, they tried to leverage this ages vision that the NT kernel would be the super kernel able to translate any kind of syscall. So what they did was essentially a syscall translation layer. So you would have your applications thinking that they are running in Linux, but it was actually the Windows kernel that was executing all those syscalls. Of course, that's very hard to maintain. But this particular architecture has one advantage, which is the speed in the file system access. So this is the kind of workload that keeps the WSL 1 still alive. The only recommendation I could give you in your case back then would be to keep your stuff inside the WSL, compile everything there, because it would be a little bit faster. Because you would only manage the disk side. But going through Plan 9, then you're doing networks.
Well, I was using it inside WSL. But even then, I mean, the root file system that you're using WSL is just mapped in a file in the WinFS. Yeah. So you're using Plan 9 every time. So this is very bad design. I mean, at least for performance, of course. I mean, if you're just a regular user, I'd see no problem. It worked quite well. But if you try to build anything,
if I had to bet, but there is no roadmap about that and nothing public that's written. But looking at the more recent changes that happened in the WSL repository, mostly driven by Docker, they implemented something together with Microsoft about VirtIO for networking.
Exactly. Yeah, I mean, they can use vSOC, for instance, which is way more performant than Plan 9, and can do that as well. So, yeah, anyway.
I guess it's something to look forward, but it's nothing that is on any public roadmap, as far as I can tell.
All right. Any other questions?
I have a question. I think you
almost replied, but in WSL2 there are a real Linux kernel running somewhere, or just call translations to straight to the Windows kernel.
With WSL2, it's a real Linux kernel. It's a virtual machine. It just happens to be a managed and quite optimized virtual machine, so we don't see all those layering details, but it's Linux. And the current version, I think, is 6.6 point something, so it has quite recent features. You can do I/O ring, for instance. It's quite nice.
Okay. Is it the same kernel instance for all distros you are running, or it's a new VM for?
Excellent question. This is kind of a performance optimization, let's say. The way they architect WSL, you have one VM per Windows user. So your Windows user has one VM. And if you spawn many Linux distro instances, those are actually containers. So they think they are a full virtual machine, they are actually containers. So you have a container of Ubuntu and a container of Fedora and a container of Arch running on top of the same kernel. Then you know what to expect from this.
I believe there's no LXC for Windows, right?
Yeah.
But that's similar, right?
Kinda. Yeah. It's the closest we can get.
Yeah.
You can still run LXC on top of an AWSL instance. Nowadays you can even do nested virtualization.
All right, cool. Thank you very much.
Thank you.
We will be back at 1:15.